Hello everyone. In the previous video, I mentioned that the focus of this chapter is going to be on understanding the firm's cost minimizing behavior given a certain level of output. So, just to do this section should be a little bit familiar for you, given that we've seen something similar in the utility in the consumer theory part of the course. So we're now looking at a case where labor and capital are the two inputs that are being used. And we're told that the firm has already decided what output it wants to produce. And let's call that Q naught. So the goal is to produce a certain level of output Q naught, and we want to identify that level of capital and labor to use, which will be the least cost combination of inputs ever in order to produce this output. So we're going to identify those values of K and L, which cost the least amount for us. And they also enable us to produce this Q naught level of output. So our problem boils down to something like this. Now, my ISO quant is given here. And I'm just going to have a series of ISO cost lines or budget lines. Just pardon my poor drawing skills there. So I have a series of ISO cost lines or budget lines. My goal is to identify that budget line, which is tangential to my ISO quant, and also happens to be the lowest possible budget line that is tangential to my ISO quant. Turns out, in this case, that solution is given by the line that I'm highlighting right now, this ISO cost line. And that point where you see the tangency between the ISO quant and the ISO cost line determines how much of labor and capital will be hired. So before we go further, let's just understand the mathematical nuances of what's happening here. If I call this point, say, E, at E, the ISO cost is tangential to the ISO quant. If they're tangential, then it means that they're going to have the same slopes at that point. Well, the slope of the ISO cost line is nothing but the negative of the price of labor over price of capital. And we know that the price of labor is W, the price of capital is V. We also know that the slope of the ISO quant is just minus dk by dl. Sorry, it's just dk by dl, not minus dk by dl, which is nothing but minus MPL over MPK. And by just looking at the graph, we know that at point E, these slopes should be equal to each other. That means W by V minus W by V will equal minus MPL over MPK. You can just cancel out the negative signs, and this condition will hold at the point of, at the optimal solution. So at the cost minimizing choice of inputs, the ratio of prices of these inputs will also equal the ratio of their marginal products. So let's study this more systematically. Now, let's consider a firm's ISO quant. Just like we've discussed before, the minimum cost combination will happen at that point where the rate of technical substitution, this is nothing but MPL over MPK, where the rate of technical substitution equals the ratio of prices of the two inputs. Intuitively, rate of technical substitution tells you how much of one input you're willing to give up to get one more unit of another input to stay on the same ISO quant. The price ratio tells you the relative value of the two inputs in the market, how you can trade one input for another in the market. So this rate of trade-off in the production process, the rate of trade-off between the inputs in the production process should be equal to the rate of trade-off for the inputs in the marketplace. Let's see why intuitively this should be our optimal solution. So the way we do that in theoretical economics is we'll try to move away from this optimal point and see, understand what happens in that non-optimal point, and then figure out why we don't want to move away from the optimal point. So this process of understanding a phenomenon is called comparative statics. So let's see that. Suppose a firm produces an output level of Q naught by using 10 units of capital, 10 units of labor, and suppose we are given that the rate of technical substitution at that point is equal to 2. Meaning they can give up 2 units of capital to get 1 more unit of labor while still producing Q naught. We're also given the prices of labor and capital, they're both equal to 1. The units are immaterial at this point. Now RTS is equal to 2, but W by V is equal to 1 by 1. So we are having a scenario where the rate of technical substitution is not equal to the price ratio. Hold that thought. The cost of production at this particular point, where we're using 10 units of labor and capital each and paying the cost of each is just 1 per unit. The total cost works out to be 20. Now, why is this not an equilibrium point? Let's see. Well, we're told that the rate of technical substitution is 2. So at that point, the firm can actually give up 2 units of capital to get 1 more unit of labor. So they can actually move to using 8 units of capital and 11 units of labor and still produce Q naught by definition. Now, when they move to the different K and L combination, if the prices of the inputs remain constant at 1 each, the total cost of production is now going to drop to 19. What does this tell us? We're still in the same output. We haven't changed the level of output. We've just changed the capital labor combination. And we've actually gotten to a point where the cost of production now is lower than what it was earlier. That is just telling us that we were not at the optimal point initially to begin with. And that is being reflected by having this, by defining the optimality condition to be this equality. As long as your RTS is equal to your price ratio, your optimal production happens there, or your cost minimization happens there. If this if this equality doesn't hold, then you're not optimizing in the first place to begin with. So let's also see a quick numerical, let's also do the calculus version of, let's see how we get this result from calculus as well. Our goal now is to minimize costs given a certain level of output. So our objective function is actually to minimize costs equals WL plus VK, subject to a constraint of having to produce Q naught levels of output. So we're going to just write down the Lagrangian function and solve this. So how does that look like? When I set up the Lagrangian, I have the objective function, WL plus VK, that's just my cost function. And then I add a lambda, and within the brackets, the constraint shows up as Q naught minus F of KL. Now we're going to assume that we're in a world where isochrones are convex. So just the first order conditions for the Lagrangian solution are going to be enough for us to get to the answer. So first order conditions would mean taking the derivative of the Lagrangian with respect to L, K, and lambda, the 3 inputs into the Lagrangian function. So let's take a derivative with respect to L. You get the first condition there. If we take a derivative of the Lagrangian with respect to K, you get V minus lambda times dou F over dou K. And we set each FOC equal to 0. And then the last one is when I set the Lagrangian, the derivative with respect to lambda equal to 0. And that just gives me back my constraint. Now our focus will be on the first 2 FOCs. Okay. So if I divide the first 2 FOCs, I'm just going to be looking at W equals lambda times F sub L Then in the second one, I have B equals lambda times F sub K. If I divide these two, then the result that I get is that W over V equals FL over FK, which is nothing but the rate of technical substitution. This is exactly what we saw graphically, intuitively, and now mathematically also. So any cost minimizing firm should equate this ratio. There are a couple of other intuitive explanations to this underlying this particular expression as well. So we have W over V equals FL over FK. There's another way of thinking about this. If I just cross multiply the terms, I get this particular expression. I get Fk over V equals FL over W. Now, what is each term telling us here? Fk is the marginal product from one more unit of capital. V is the cost that I have to pay to get one more unit of capital. So Fk over V is just the marginal product to marginal cost ratio. How much more output am I getting by spending money on getting one more unit of that input? Similarly, FL over W tells me how much more output am I getting additionally by spending money on hiring one more unit of labor. Well, for a firm to be cost minimizing, these ratios have to be equalized across all inputs. So the marginal productivity that I get from that input, for every dollar that I spend on that input, this ratio should be the same for all inputs. What happens if that were not the case? Suppose if Fk over V is greater than FL over W, then it means that capital is more productive. For every dollar that I spend on capital, I'm getting extra in addition to the output than what I would get from labor. So it makes sense for the firm to get more of capital and less of labor. So they were not finding the cost minimizing bundle in the first place. And you could use a similar rationale when the inequality goes in the other direction. So that's another very intuitive interpretation that we get from this condition for cost minimization. Another point is where we're just going to flip this relationship. We're just going to flip it upside down. And what do you get? We get the ratio that W over FL, and that should equal V over Fk. And this ratio is actually equal to lambda, our Lagrange multiplier. So W is the marginal cost of hiring one more unit of labor. FL is the marginal product from one more unit of labor. So this is the cost to productivity ratio. Similarly, this is the cost to productivity ratio for capital. Now, this ratio tells us by how much our costs, if we were to increase our output marginally, how would our marginal costs go up? Well, in equilibrium, this ratio has to be equal across all the inputs. That's what our condition tells us. And this ratio will also be equal to the value of the Lagrange multiplier. And the Lagrange multiplier, if you remember from our utility maximization story, in that scenario, what did it tell us? It told us by how much our objective function will change whenever there's a small change in the constraint. So if we were maximizing utility subject to some budget constraint, it told us by, if your budget constraint goes up by $1, if you have an additional $1 of income, by how much would your optimal utility increase? That's what lambda gave us then. In this scenario, the similar interpretation holds. Lambda tells you that for a small change in your constraint, our constraint now is the output that we need to produce. So for a small change in that constraint, by how much will my objective function change? So for a small change in output to be produced, by how much will my costs change? So it just measures the extra cost to be incurred if we were to increase the output marginally. So that's what lambda tells us here. Now, very quickly, we'll review this story using a graphical analysis. And I'm going to run through this slide very quickly because we're already familiar with it now. So the point to note is that the cost minimization happens at that point where your isoquant is tangential to the lowest possible budget line. And the cost minimization happens when we choose KC levels of capital and LC units of labor. There is a reason why we put a C subscript there for the inputs. And that's because the amount of capital and labor that we're choosing here depends on the level of output that is being produced. If the level of output changes, I'm going to be needing different levels of K and L in order to achieve that output. So K and C that we're finding here from cost minimization are actually contingent upon the level of output that is being produced. And therefore, these demand functions for K and capital and labor, we denote them with a superscript of C, just to show us that they are dependent on the level of output being produced. So I'm out of time for this video. So I will go with the next concept in another video. See you there.